And as many mafic, ultramafic sills, here in red is coeval with the end Permian mass extension. So the material of the study was obtained from a well pH 265, which is located in the middle part of the Norilsk 1 intrusion. And as the other world-class deposits like Karayalakh and Talnakh is controlled by the Norilsk Karayalakh regional fault. The structure of the Norilsk the intrusion is resembles a lopolith, elongated lopolith, which extends roughly for 14 kilometers on its axis. And the coin term for this structure is chronolith. Here we can see typical economic intrusion. The mineralization is mainly located at the bottom of the intrusion, and it can be either massive or disseminated or even veins. The intrusion was in place below a thick basalt sequence of Triassic age into sedimentary sequence of Tunguska series containing coal and evaporites. So concerning the mode of emplacement and crystallization of the Norilsk 1 intrusion still remains inconclusive whether it forms from one magma pulse or actually different magma pulses. So these are like the main postures for the trying to explain the anomalous compositional and textural changes in Norilsk 1. And well, these are like the main flaws that each of the hypotheses needs to overcome or needs to explain to address, from which I highlight, for example, in a single magma pulse. So the mineral compositional reverse is something that needs to be coincide with this hypothesis, or in the two or more discrete magma pulses, for example, there's a very low probability of different pulses stacking in such orders, which can be explained by fractional crystallization. So the work of Latipov, he has been trying to defend this hypothesis from 2003 by invoking a mechanism of thermal boundary layer and Sorek effect. And more recently, Yao and others has proposed this assimilation batch crystallization mechanism to explain most of the compositional trends in mafic, ultramafic layer intrusions. Additionally, Latipov in 2008 added that the compositional reverse in cyclic units can be accounted as an evidence for the origin from separate pulses of magma. So these are the methods I use divided into petrographic, numerical, analytical. So now let's take a look. This is the Norilsk 1 generalized layering, and this is the actual internal zoning of the well pH 265, comprising from bottom the basalt host rock and the main ore horizon units, which correspond to the study interval. These are 3 hand view samples from the units of the main ore horizon, which at first glance differ from one another. So we're gonna see into more detail. So basically here, I just wanted you to have in mind the position of the units. So we have this olivine chromite earth accumulate at the top, known as the picritic gabbro-dolerite. Then we have the taxitic texture gabbro-dolerite, and then at the very bottom we have the olivine bearing gabbro-dolerite. So the picritic gabbro-dolerite has mainly poikilotic texture with accumulates of olivine greater than 35%. We have chromite less than 5%, and plagioclase is normally less than 10%. The taxitic texture gabbro-dolerite is characteristic for having highly heterogeneous texture with accumulates of plagioclase greater than 60%, and olivine is less than 10%. It is thought it is thought that it is this taxitic texture represent remobilized crystal mass from the magma column. This table summarizes the main mineralogy for each of the units. And at the last, we have the olivine-bearing gabbro-dolerite with subophytic texture, which becomes more intergranular towards the chill margin, with accumulates of plagioclase and an olivine less than 5%. This is a preliminary assessment of the oxides zoning. So we found out that chromite only occurs in the picritic gabbro-dolerite, and it shows modal reverse with very low modal amounts, less than 1% at the bottom, and up to 6% of chromite at the top. Additionally, we found that ilmenite occurs mainly in taxitic in the lower units of taxitic and olivine-bearing gabbro-dolerites. The main compositions of chromites are iron chromites and aluminum chromites. The chromium number is variable, and the ratio of iron 3+ and 2+ is higher to the bottom, which indicates probably higher, more oxidizing conditions. And we also have more primitive chromites at the bottom. Both of oxides, chromites, and ilmenite are closely associated with sulfides and PGMs. Now let's have a look to the transitional zone and hybrid nature rocks. So just above the contact between taxitic and picritic rocks, there's an interval I call the transitional zone, because of the ores and the textural features here represent kind of a mix of both of these units. In this transitional zone, we have no chromite, we have a low modal olivine, and we have higher modal plagioclase. So we compare this with a typical picritic rock, so we are going to have here a little bit of different values. Chromite starts occurring from this sample 62 and upwards, mainly as the inclusions in olivine. So now let's have a look here. This is the contact between taxitic and picritic gabbro-dolerites. If we have a closer look to the contact, so we go from a typical taxitic rock in number 70, and in number 69 we have kind of this transitional picritic rock. In this transitional picritic rocks, we can find structures like glomerocrest of olivine, varying in size. This is very typical. In this transitional interval, we also have this sample 67, which exhibits a flow texture, which we're going to see in more detail. And also the samples have significant amount of glomerocrest, for example, of plagioclase, compared with the rest of the picritic interval. Additionally, we're going to check this very thin layer of chromium-rich taxitic gabbro-dolerite that occurs within the picritic layer. So this is the presumably hybrid nature rock 36, which occurs here within the picritic gabbro-dolerites. As you may see, it has important amount of chromite, up to 5%. Olivine is less than 10%. The rock is highly altered. Sulfide, would not say it is a low sulfide compared with the rest of the section. It has the highest PGE content in the whole well pH 265, and it's a very thin layer of probably very fractionated melt. So the gas bubble structures here, they're not pretty clear. However, we can check this close up I make. So there's some kind of circular structures. Some of them they contain sulfide. So I just draw something here like this. So they're not really as evident as in the low sulfide in the upper part. However, we can see, and we have also this reaction rim with the clinopyroxene, where we have a coarse grained chromite growing. And this is a closer look to the hybrid nature rock here in the transitional zone. This is an olivine gabbro-dolerite. Basically, we have here less than 15% olivine and 30 to 40%, so it's more fractionated than epicritic. We have these probably grain scale convection cells at the contact of these two units, probably associated with the high thermal gradient and related with marginal mixing. Or this can even represent the cumulus pile magma interface. Additionally, this sample exhibits some texture which resemble these gas bubble structures, like for example, right here and here, where they are infilled by hydrous phases and carbonic phases like calcite, siderite, etc. This sample with flow texture is low in sulfide. It has important PG, and also it has no chromite, only ilmenite occurs here. So, and here, well, we can have a closer look to one of these bubble structures. So now let's check the composition of the primary silicates. So basically, plagioclase classified as bentonite and clinopyroxene as augite, hyperstein. However, the most important here is that both orthopyroxene and clinopyroxene, they show compositional reverse with more primitive compositions in the epicritic gabbro-dolerite. We can also see the compositional reverse occurring for olivine, where a more primitive compositions in the epicritic in the upper part of the main ore horizon. This is a vertical variation on the composition of plagioclase, pyroxene, clinopyroxene, and olivine. At first glance, we can see that there is a significant variation between the rim and the core in plagioclase for taxitic rocks, while in epicritic gabbro-dolerites, this variation is much less. Also, at the contact, we can see, for example, a variation at the contact between taxitic and epicritic rocks. We can see variation of 7%, for example, for the rim. In pyroxene, we can see a variation of 6%, and for olivine of 4%. So all these abrupt changes in the context, so we will see how we can gather all this information. Additionally, for clinopyroxene, we can see that in epicritic gabbro-dolerites, these are more chromium rich compared with taxitic ones, and in the lower units of taxitic and olivine gabbro-dolerites, these are more manganese rich compared with epicritic ones. A similar trend was found for olivine, with more evolved compositions at the bottom in taxitic rocks. And also plagioclase, we found some minimum contents of potassium, which may indicate some new pulses or magma replenishment. And these minimum amounts of potassium are related with some textural features. Additionally, we also found zoning in pyroxenes and clinopyroxenes and plagioclase, probably related with the very dynamic magmatic conduit system, as mentioned by Schonveld and others in this 2020. Maybe suggesting an open system or anticrest. We observe a lot of normal zoning with abrupt variations between core and rim. When investigating the ores, we found out also there's breaks in the compositions occurring at the contact between epicritic and taxitic gabbro-dolerites. What is remarkable here is that the hybrid nature of rocks or samples like 36 and 67 diverge from the main trend of epicritic gabbro-dolerites towards compositions more close to taxitic rocks. And the same was observed for pentlandite, for pyrrhotite, and chalcopyrite. Additionally, the composition of the ores suggested high temperature composition or phases in the epicritic gabbro-dolerites and higher fugacity conditions for the taxitic and olivine-bearing gabbro-dolerites. at the bottom. So we found these two associations of high sulfur with comprising nickel-rich pentlandite and monoclinic pyrrhotite, and in picritic we found this low sulfur association of iron-rich pentlandite with troilite mainly. Similar results were found by Nickel and Harris in 1972. Where they concluded that the iron-nickel in natural samples, they concluded that the iron-nickel ratio decreased with the increase in sulfur fugacity. We also investigated the PGMs, and we found out that there's a compositional distribution for the palladium compounds, where the high temperature palladium compounds are located at the top of the layers of the units. And the role of chalcogenes starts increasing downwards. So we found more low temperature compositions at the bottom. In this sample, the zoning is not so well, is not so evident. However, we will see in next. Here is also important to remark that samples 36 and 67 of hybrid nature show the highest variety and modal amount of PGMs, probably related with their hybrid nature. So we did we published an investigation where we studied more boreholes and did more analysis, and we actually were able to infer two different thermal gradients for the picritic gabrodolerites in the upper part and for the lower taxitic and olivine gabrodolerites. So if anybody's interested in this paper, so I'll be more than glad to share it with you guys. Now the geochemical zoning of the rocks. So we basically found that there's a correlation between the petrographic or the textural features of the rocks and the sulfur content and the ore metal peaks. So we basically found there's some positive correlation, which might be associated with multiple magma events or replenishments of magma in the magma chamber. Additionally, we found that the taxitic and olivine bearing gabrodolerites are characteristic for having a nickel copper ratio less than 1, while picritic rocks are typical for having nickel copper greater than 1 in average. And finally, so this is the concentration of ore metals in 100% sulfide. These patterns for the 3 units suggest the similar fractionation trends suggest a common source. However, there's some differences between picritic and the other 2 layers, showing higher ore grade and probably related with the evolution of the sulfide liquid, maybe a higher R factor, maybe the sulfides were formed in situ or entrained. And this is a summary of all these features, suggesting the formation of the main ore horizon basal reverse from at least 2 different magma pulses, differing in composition and crystallizing under different conditions of temperature and sulfur fugacity. So we have this primitive pulse at the top, and you have more evolved pulse at the bottom, with all the characteristics I mentioned before. So finally, this is like the question. So these are what are the evidences for the different magma pulses? So we have different sulfide associations. We have 3 different very distinct types of rock by the texture and model composition. We have oxides zoning, chromite occurring in picritic gabrodolerites, and ilmenite occurring in taxitic rocks. We have reversing model chromite, and also the chromite horizon is located at the top, which is difficult to explain by means of pure fractional crystallization. We have this compositional zoning of PGMs. We have compositional reverse of Klein pyroxene plagiar class. We have breaks and sharp changes in the composition at the picritic and taxitic boundary, and so on. So I think that most of the results are in good agreement with an evolution from multiple discrete magma pulses, at least 2 for the main ore horizon. However, we do not fully discard the possibility of explaining this from by means of fractional crystallization in a more dynamic setting. That's it. Thank you very much. Now I'm ready for any questions, maybe.